Alright, let's have a test review. All moving objects have momentum. Momentum is a product of its velocity and its mass. At least for most things. Later in the year, we'll see that even if you don't have mass, you can still have momentum. Like, for example, photons of light have no mass, but they still have momentum. But for ordinary objects, momentum, represented by the letter P, is equal to its mass times its velocity. Objects that are moving also will have kinetic energy. We've already learned about kinetic energy. And if they're moving, they obviously have some velocity. So, this relationship, this equation, momentum depends on the product of mass times velocity. If you double the mass, you double the momentum. You double the velocity, you double the momentum. If you double both, you quadruple the momentum. We also have the notion of an impulse. Impulse is simply the change in momentum. Or an impulse is equal to force times time. I'm
so sorry, but he's been every day next week over my spring and I got put off. That's where I am with that.
What I do with if he needs a physical help.
Thank you.
Mm-hmm. So, impulse is basically related to how much force is applied for a given amount of time. If you double the time that force is applied, you double the impulse. If you double the force for a given amount of time, you also double the impulse. Here's a fun fact. If you've ever played video games like Call of Duty, you've probably seen that when you add a suppressor, sometimes called a silencer, to the end of a gun, it reduces the damage of the gun. In real life, this is wrong. Let's think about it. So, we have a gun. We have a bullet. And we have the barrel. It goes down. Whenever you pull the trigger, the primer explodes. And a lot of pressure is built up. Pressure is just force over some area. And in this case, it's the area of the end of the bullet. Or the back end. So, this force is being applied to the bullet over the distance of the barrel. If you were to add a suppressor or a silencer to the end of a gun, you're making the barrel longer. This means that the gas explosion is now applying over a longer distance and over a longer period of time. So as this gas expands and pushes the bullet, you're basically increasing time. Force is also decreasing as it expands, but time is increasing more than the force. So the impulse, when you add a suppressor, the impulse will increase, and thus the bullet velocity will also increase. This means that if you add a suppressor to a gun, the bullet travels faster and has more kinetic energy. Overall, suppressors can only improve the quality of a gun. It reduces noise, meaning that it doesn't damage your ears. The increase in barrel length increases the bullet velocity, so since if it's going slow, it'll drop off quicker, but if it's going really fast, it'll be able to go longer distances and have a more straighter flight time. So, the average force won't change too much. Let me see if that's right. I believe most of the time, the impulse, though, will increase. So the average force will go down. So the average force will go down a small bit, but the total time will increase significantly more, and so the total impulse of the bullet will increase. And thus, equivalently, the change in momentum will increase. So bullets travel faster. Likewise, let's compare the scenario of a car running into a bale of hay. It has some mass and some velocity. So the initial momentum is mass times its velocity. And after it runs through the hay, let's say it comes to a stop. So here it's now 0. It has no momentum. However, the time it takes it to stop, so there's some time for it to stop, will be significantly longer than the scenario in which it runs into a brick wall. Imagine you have a car, brick wall, spinning at V, M. So it has an initial momentum of M times V. Then when it hits the wall, let's say this is an immovable wall, it stops. So the change in momentum is it goes from mv to 0, mv to 0. So the impulse is going to be the same in both scenarios. So the change in momentum would be 0 minus mv. Change in momentum is 0 to mv. So the impulse is negative mv. But what's different between these two scenarios? Here, because impulse is equal to force times time, if time is significantly large, then the force felt on the car is going to be small to counteract it. If, on this scenario, you come to a stop very quickly, so very short time, that means the force has to be equally as great, as this is small. The change in momentum is the same, so same change in momentum. same impulse, but different forces and times. That is what's different between these two scenarios. So here's another scenario. Suppose you drop a coffee mug onto carpet versus a marble floor. What's different about this scenario? Well, if you've ever done this, you might know that the coffee mug will probably shatter on the marble, but it won't break on carpet. Why is that? Well, it's going from having some speed, so if they're dropped from the same height, so if it starts from some height h, it's going to have some potential energy. That potential energy will be converted into kinetic energy, so at the bottom, it'll be the same velocity. So they'll hit the ground with same velocity and momentum. But what changes? On a carpet, you have fibers, and as the mug hits, these fibers act like little springs. They'll exert a small force onto the mug, and the time it takes for it to come to a stop will be significantly longer than if it were to directly hit a rigid surface at the very bottom like this. This begins to slow down between this time, while this slows down right here. You might even chip the marble floor if it's a tile floor. You might even have the tile on the ground break and also the coffee mug break. So in this case, large force, small amount of time. Here, relative, we have a large amount of time and small force. Hence the reason why a coffee mug or a glass bottle might survive a drop onto carpet, but break on a wooden or tiled surface. But the change in momentum, they're going from having some momentum to zero momentum. So this started out with mv, and the moment it stops, it goes to zero. Even worse scenario would happen is if it bounces. So if it hits the ground and bounces, it's going from having a momentum downward, mv, to a momentum upward, mv. And this means that the change in momentum would be 2 mv in the upward direction. And mugs don't usually bounce on carpet as well. So even in this scenario, it's going to be less. But if we ignore bouncing, they'll have the same momentum. Eventually, the momentum will stop. It will stop bouncing.
Bambi, if you're on campus, can you come up to the front office with Bambi?
So let's compare this generic example. We have a box. Let's say it's A, and another box B, and let's say this is moving at some velocity. let's say they both have a mass of m, and let's say they stick together. When they stick together, their masses will combine, so they'll have 2m. When they stick together, this means it's going to have to be inelastic. There has to be some energy converted from, so some of the kinetic energy has to go into causing them to stick together. Inelastic means that there is loss of kinetic energy. It's converted usually into heat, sound, and other things. And I'll say this is V1, and this is V2. Because, so, momentum doesn't change, so the total momentum, so the sum of momentum here, this would be the sum of initial momentum, has to equal the sum of momentum on this side, the final momentum. Because this has no speed, it would have zero momentum, so the momentum over here would be m times the initial velocity. But on this side, the mass is doubled because they're now sticking together. What this means, because mass increases, so if we started out with m times v, and if we were to increase mass, then the velocity is going to have to decrease for these two to be equal. So this speed will be less than the initial, it'll slow down. Note that energy is always conserved. Just remember that inelastic collision means that kinetic energy is not conserved. For the test, you'll have to memorize these two equations. P equals mv, P represents momentum, and J equals delta P, or J equals Ft, or you could even span this out into M2 V2 minus M1 V1, final minus initial. You can combine these two. F times T is thus equal to delta P. You need to know that the units of momentum, so looking at the equation, mass is kilogram, velocity is meters per second, so the units of momentum is kilogram meters per second, and because impulse is equal to change in momentum, it'll share the same units. Which has more momentum? A large boulder? Or a grain of sand? This is not enough information. It depends on the mass and velocity of each. A grain of sand could in fact have more momentum than a boulder. It's very easy to see this. If a boulder isn't moving, it has zero momentum. And if a grain of sand is moving with a non-zero speed, it has something greater than 0 and thus more momentum. You might have seen parkour jumpers jump from very great heights and land without getting hurt. If you've ever seen these people do this, you might know that whenever they jump from a very high height and land on the ground, what they do is as soon as their legs begin touching the ground, they bend their knees and roll forward. As they begin rolling forward, what they're doing is increasing the time it takes them to come to a full stop. So as they begin to roll, I can't draw. They roll forward, turning around in a circle, and basically slowing down over a longer period of time it takes for them to come to a stop. So this decreases the forces on their bones and body. This is why airbags save lives. If your steering wheel were to have this balloon come out, as you move into it, slam into it, this this compresses slightly and makes the time it takes you to come to a stop significantly longer. Another unit of impulse. So impulse is the units of impulse is usually the same as momentum, kilogram meters per second. It should be noted, if we look at this equation, so impulse is equal to Ft, force is in newtons, time is in seconds, and impulse can also have the units of Newton seconds. There will also be a lot of problems on the test where you have to do conservation of momentum. So, for example, if you're not moving, so if you weigh 50 kilograms and you're holding a 5 kilogram mug and you're not moving, you have 0 momentum. And if you throw the box, you'll start moving to the left and the box will start moving to the right. And let's say the box is moving to the right at 10 meters per second. You can apply conservation of momentum. So mass times velocity would equal 0 would equal 50 kilograms times your velocity plus the 5 kilograms times 10 meters per second. Conservation of momentum. Just solve for V. So your momentum, so moving this over, that'll be negative 50 kilogram meters per second equal 50 kilograms times velocity divided by 50. We get negative 1 meters per second is equal to your velocity. There'll be several problems where you have to do that. I haven't really done this But average force, if I say, what is the average force? It's just solve for force, ignore the word average. We just, when I talk about asking for solving average force, we just assume that force was constant during it. This will be all multiple choice. Keep in mind direction. So, for example, if a ball is initially going this direction, then later it's going this direction, the overall net change will be overall. We have to push on this, make it slow down. We have to push again to make it come to a stop. Then we have to push again to make it go to the left. So the overall change will be in the direction left. So the leftward direction. So like for example, in a bounce, if you're moving downward with MV, then you bounce off going up MV. So this is your final. This is your initial. So the change is final minus initial. So that would be MV upward minus MV downward. And if we let upward be positive, this would be MV, and downward be negative, so that would be negative MV. These become positive, so we get 2 MV. Positive means upward, so 2 MV upward. Likewise, if a ball is moving upward at MV, it goes up and stops, then comes back down at MV, then hits the ground at some very great speed, and then bounces back upward, and is moving at MV right here. If we only compare this one and this one, the change in momentum is 0. Because they're both the exact same value, they're both in the same direction. And one more example. Suppose a box. Let's make this 5 kilograms, moving to the right at 1 meter per second. This is 10 kilograms, moving to the left at 2 meters per second. They collide on each other and end up with this. So this one's moving to the left at 1 meter per second. And this one is moving to the right. They just perfectly bounce off of each other. Let's say this one's going at, let's say 1 meter per second. Is this inelastic or elastic? So to see that, we have to see if any total momentum has changed. Oh, and let's make this, let's change these values. Oh, that should be good. So the total momentum on this side would be 5 kilograms times 1 meter per second. So 5 kilogram meters per second. I'll let right be positive. So